Every instinct tells us that time is the one thing in the universe that never hesitates. Seconds tick forward, hearts beat, stars age, and every memory we possess is arranged along a one-way river from past to future. In ordinary life, time feels absolute, relentless, almost mechanical. You never wake up to find yesterday returning, nor do you ever sense the universe pausing between one moment and the next. That intuition is exactly what makes the question so unsettling. Can time actually stop? At first glance, the answer seems obviously no. A stopped time would appear to freeze everything: motion, thought, even the process of asking the question itself. If nothing can change, how could anyone inside that frozen reality ever notice it? This is the first powerful contrast between human intuition and physics. What feels impossible to experience may still be perfectly meaningful as a description of reality. The first crack in our common sense picture came with Einstein. Before relativity, time was treated like a universal stage flowing identically for everyone everywhere. But Einstein replaced that certainty with something far stranger. Time depends on motion and gravity. Two observers moving differently do not necessarily share the same duration between events. Even identical clocks can disagree. This means time is not the unstoppable cosmic metronome our senses suggest. It can stretch. It can compress. Under the right conditions, it can slow dramatically compared with someone else's frame of reference. The faster you move, the more your time separates from the time of a stationary observer. The stronger the gravity around you, the more slowly your clock advances relative to distant space. So the real mystery is no longer whether time feels unstoppable, but whether that slowing process has a final limit. If motion gravity can keep reducing the rate at which time passes, could the flow eventually shrink to nothing at all? And if it could, would time itself have stopped, or would reality simply look that way from somewhere else? See, that distinction between what an observer experiences and what another observer sees the doorway into the deepest part of the story. Time may never stop in your own frame, yet from outside. It can seem to crawl towards stillness, to understand whether that limit is real or not. The idea that time can slow is already strange, but physics pushes it far beyond intuition. According to Einstein's relativity, the rate at which time passes is tied directly to speed. The closer an object moves to the speed of light, the more slowly time passes for that object relative to someone at rest. This is not illusion, bad measurement, or clock malfunction. Time itself genuinely stretches. Imagine a spacecraft accelerating closer and closer to light speed. For the travelers inside, everything feels normal. Their hearts beat at the usual rhythm, their thoughts unfold naturally, and their onboard clocks tick 1 second at a time. But to an observer watching from Earth, something extraordinary happens. Those seconds begin to spread apart. The ship's clock appears slower, its motions more delayed, as if reality itself is resisting forward progress. Okay? This creates the first major contrast. Inside the system, time never feels frozen. Outside the system, it can seem to approach stillness. The faster the ship moves, the stronger this contrast becomes. At Joule of light speed, years for the travelers might correspond to centuries outside. Push closer still, and the outside observer sees the ship's time rate shrink towards zero. Gravity creates an even more dramatic version of the St. M effect. Near a massive body, space-time curves, and that curvature changes the rate at which clocks run. This is why clocks on satellites tick slightly differently from clocks on Earth. But near a black hole, the effect becomes extreme. As an object approaches the event horizon, a distant observer sees its clock slow more and more. Okay? From far away, the falling object never quite seems to cross the horizon. Its light becomes redder, dimmer, and more delayed until the final moments stretch almost infinitely. To the outside universe, the object appears suspended at the edge of time itself. And here the deepest retention question emerges. If the rate keeps decreasing forever, is that any different from time stopping? Mathematically, relativity suggests an asymptotic limit. Time can approach zero passage relative to another frame without ever becoming literally zero in its own local experience. No? That means stop time depends entirely on perspective. For the falling observer, time continues normally all the way through the horizon. For the distant observer, it seems to freeze forever. Physics, therefore, forces a profound contrast between reality as experienced and reality as observed. The real question is no longer whether time can slow, but what it even means for two equally valid observers to disagree so radically about whether a moment is still moving. Once physics allows disagreement itself, the mystery becomes philosophical. If one frame sees endless motion while another sees eternal suspension, then stopping may not be a property of time alone, but of change, causality, and ultimately the observer's place within reality itself. Once relativity allows time to appear almost frozen, the question becomes far deeper than clocks. If time truly stopped, change would vanish with it. No particle could move, no atom could vibrate, no neuron could fire. Thought itself depends on sequences of events, and sequences require time. In that sense, a universe with completely stopped time would not merely be silent. It would be physically incapable of producing any experience at all. Okay? This creates the final contrast framing of the story. Time as measurement versus time as change itself. A clock stopping is trivial. Reality stopping is something far stranger. Without temporal progression, cause can never lead to effect, which means causality collapses. Nothing can happen because happening is simply another word for change across moments. But relativity gives us a subtle answer. Physics rarely says time becomes exactly zero for any local observer. Instead, it says the rate of time can become arbitrarily small relative to another frame. From far away, an object near a black hole may seem trapped forever in its final approach, suspended in an endless present. Yet for the object itself, time continues, and crossing the horizon remains unavoidable. So can time actually stop? In the strictest physical sense, probably not in any frame that still allows an observer to exist. But reality can absolutely create situations where time becomes so stretched that from another perspective, it is indistinguishable from stillness. Okay? And that may be the most unsettling conclusion of all. Time doesn't need to stop universally to stop meaningfully. If change disappears from your frame, reality ends for you. If it disappears only from someone else's frame, then time has become a question not of existence alone, but of perspective. So perhaps the deeper truth is this: time is not a universal river at all. It is a local experience of change. And under the most extreme conditions in the cosmos, that experience can be pushed so close to zero that the difference between slowing forever and stopping entirely becomes less about physics and more about what reality itself is allowed to mean.